Okay, so in this video we're going to solve a minimum cost flow problem. So we're given this directed graph. It looks like we need vertices A and B to send 10 units of flow. We need vertex D to receive 20 units of flow, and we want to do this minimizing the total cost, and the costs are given by these red numbers here. And we're also given that the capacity for edge BD is 5, and the capacity for the rest of the edges is infinity. Okay, so we're going to do this using the network simplex method. We're given that this initial basic spanning tree is going to be BA, AC, CD. So let's sort of calculate what is our initial basic feasible solution. And it's easy to do that since this is a tree. Well, our solution is going to look like this, and B needs to send 10 units of flow total, so this arc has to receive 10 units of flow. A needs to send 10 units of flow total, so it's receiving 10 already, so this arc needs to have 20 units of flow going through it. And C is a transshipment node, so it's getting 20 units of flow. It needs to send 20 more units of flow out. So this is our initial basic feasible solution, and let's see if it's optimal. So how could it not be optimal? Well, one of the non-basic variables maybe could be increased, and our cost could decrease. So what are our two options? We need to see what happens if we increase the flow going through arc BD, and we need to see what happens if we increase the flow going through arc DA. So let's make this table here where we decide if our solution is optimal or not. So there are two arcs that we need to consider, arc BD and arc DA. And since this is a spanning tree, each of these arcs, if I add flow through one of these arcs, this is a spanning tree, so it's going to create a cycle in our graph down here. And so in this case, if I add the arc BD, it will create this 4 cycle here, so that it'll create this cycle B to D to C to A. And if I add the arc DA, it'll create this triangle here, D to A to C. And we want to know, okay, what happens if I do indeed add flow along, say, edge BD, what is going to happen to my cost? So let's look at what is the change in the cost per unit of flow. So if I add flow going through BD here, if I add 1 unit of flow going through BD, then I'm increasing my cost by 2, because that's how much it costs to send a unit of flow through BD. So I'm going to increase my cost by 2 by sending this unit. But now D needs to receive 20 units total. So if it's receiving 1 unit from here, then this means that I'm decreasing the flow 1 unit from here, so that in total the flow into D remains the same. So if I decrease flow through this arc, then my cost is actually going to decrease by 5. So this is minus 5. And if flow through this arc decreases, then flow through this arc has to decrease, because C is a transshipment node. So I'm decreasing the flow through this, so my cost goes down by 3. And same thing for this arc. I'm going to decrease flow through this arc by a unit, so my cost is going to go down by 1. So here what we're saying is that if I increase flow through this arc BD, my net cost is actually going to be decreased by 7 units. So this is strictly less than 0. Again, we can see what happens if we increase flow through DA. So if we increase flow through DA, then flow through AC is going to have to increase as well, because extra flow is going into A, so extra flow needs to come out of it. And then same thing, flow is going to have to increase through CD. So if I increase flow through DA, if I add 1 unit, this costs 4. If I add 1 unit of flow through AC, this costs 3. If I add 1 unit of flow through CD, this costs 5. So adding a unit of flow through this arc DA is actually increasing the flow through all of these arcs. It's increasing my total cost through all of them. So this is going to be 12, which is greater than 0. So we want to minimize our cost. So we do want to increase flow through BD, and we do not want to increase flow through DA. So BD is going to be our entering basic variable here, our entering basic arc. So this is our entering basic arc. I'll draw it in blue here. And we want to increase this until we find our leaving basic variable, right? So I'll say that we're going to send theta units through here. And what's happening is theta units are going through here, and we decided when we did this calculation that this means each of these three arcs are decreasing by theta units. So none of these arcs can go below 0, so this means that theta is less than 20 for this one, theta is less than 20 for this one, theta is less than 10 for this one. But how much can it increase? The capacity of this arc BD is 5, so actually theta is less than or equal to 5. So this one is the most strict condition, so this one is actually going to be our leaving basic variable. So we're in this kind of interesting situation where the arc BD was the entering basic variable, but it's the first one to reach its upper bound, so it's also the leaving basic variable. This is okay, so this is fine, but what's happening is we are increasing this theta up to 5, so we're increasing the flow of arc BD up to 5, and this is reaching the upper bound here. So we have to update our table and use this upper bound technique and sort of imagine that we're sending 5 units of flow this way, and then re-update this graph. So let's draw our new graph where we imagine that we're sending 5 units of flow this way and make a new decision variable that tells me how many units of flow am I taking back. So let's update our graph. A, B, C, D. And now the net flow is gonna be different from here because we're imagining that we're already sending 5 units of flow from B to D. So B is already sending 5 units. It needs to send 10 total. So now in this new graph, the net flow from B needs to be 5. Nothing is changing about A, and nothing is changing about C. But D needed to receive 20 units. It's already receiving 5, so now it only needs to receive 15 more units. And now all of the rest of the arcs are going to be the same, except for this one that we are reversing. And now this new arc is going to represent how many units of flow are going back here. And all of the costs are going to be the same, except this one's now negative, because this how many units of flow we're canceling out is reducing my cost, right? So this is cost 1, cost 4, cost 3, cost 5, and now this one is cost negative 2. And so the capacity of this arc UDB, the most that we can cancel out is still 5. And the rest of the capacities are infinity. And so now let's see what's happening. Our basic feasible solution now is it's still almost the same. I mean, it's the same set of arcs, but these have been updated, right? I sent 5 units this way. I had to decrease these by 5. So our basic feasible solution looks like this. A, B, C, D. Now I'm sending only 5 units from B to A, only 15 units from A to C, and only 15 units from C to D. And this is our basic feasible solution in this updated graph. So here, like, I've imagined that I've already sent 5 units this way. So this is a basic feasible solution. And now we can do the same thing. We can check, is this solution optimal? So what do I need to check? I need to check if adding flow through this arc D to A is going to decrease my cost, or if adding flow through this new arc D to B, or you can think of it as reducing flow in the previous example, is gonna decrease my cost. So let's make this table again, where I check if I add arc D to B, what's happening, or if I add flow through arc D to A, what's happening? Because these are the only 2 arcs that I could possibly add flow through. And so if I add flow through arc DB, it creates this cycle DBAC. And if I add flow through arc DA, it creates this cycle DAC. And I can ask, what is going to be the change in my objective function if I do that? What is going to be the change in my cost? And now if I look at the second line, you'll notice that nothing has changed about this cycle here. So this calculation is going to be exactly the same. Adding flow through edge D to A is going to increase my costs. It's exactly the same calculation as before. And if you think about it for a second, I mean, we can do the calculation here. What's going to happen is if I add flow from D to B, well then this is going to actually decrease my cost because the cost here is negative, right? But if I add flow from D to B, then I'm going to have to add flow from B to A because I need to keep the net flow at B the same. So I'm going to have to increase the flow from B to A, so this is going to incur a cost of 1. Same thing, I'm going to have to increase flow from A to C, so this is going to incur a cost of 3. And I'm going to have to increase flow from C to D, so this is going to incur a cost of 5. So this net cost is going to be positive as well. And we maybe could have done that without doing the calculation, because what's happening is I'm just reversing flow from before. We calculated that if I increase flow this way, it was helping me. So if I reverse this flow, it's gonna hurt me. So here we've checked for optimality, and we are optimal. Increasing any of the non-basic variables is going to increase our costs, which we're trying to minimize. So here we're at an optimal solution. So the optimal solution is send 15 units from A to C, send 15 units from C to D, send 5 units from B to A, and we're almost done, except we have to remember that this, we're not in our original graph, right? We're in kind of this updated graph where we've already imagined that we're sending 5 units this way, so we need to remember that we're sending 5 units from B to D here. And this is our optimal solution, and this is the minimum. This will give the minimum cost.